And welcome back to chaos. So we are, if you remember where we were the last time we met, we talked a little bit about the Lorenz system and its confusing dynamics. I think in particular we finally got to the concept of sensitive dependence on initial conditions. We talked about that last time, that if you have two nearby trajectories, they separate approximately exponentially fast. And we said that that exponential rate, when we have an e to the lambda t, the lambda we were calling the largest Lyapunov exponent, or just for short, we often just say the Lyapunov exponent. And we mentioned that a positive Lyapunov exponent, meaning exponential divergence of trajectories, that's a signature of chaos. Then we mentioned that the Lyapunov exponent itself gives us a time scale that is 1 over lambda, is a thing we call the Lyapunov time, or the predictability horizon. And you really can't predict a chaotic system's behavior very precisely for more than a few multiples of that 1 over lambda. There was also a logarithmic term relating to the difference between the initial conditions and also the tolerance. Maybe you remember, we have this formula. Okay, so anyway, that's where we were. And what I want to do first is be a little more precise about words like chaos or attractor or strange attractor, and then talk about a very clever thing that Lorenz did in his paper to provide evidence that his attractor is not just a very long period limit cycle. That was a question for a long time. How do you know that if there's anything really strange about your strange attractor? Maybe it's just a big limit cycle and you haven't waited long enough to see it repeat. So we'll talk about the evidence he gave, which, as I mentioned earlier in the course, is not a proof, but was very suggestive. So first to the definitions. Oh, and I won't be here on Thursday. I hope you all got the note on Piazza. So I'll be out of town, but I'll be back on Tuesday. So class is canceled Thursday. But anyway, all right, so some rough definitions. I say rough because these are not definitions like you would have in a pure math course where you could actually prove something based on the definitions. These are more like conceptual definitions so that you can understand what we're talking about, but still not quite sharp enough to do any proofs. Anyway, okay, so we keep saying chaos. So what does that mean? Here's my approximate definition. Chaos refers to aperiodic long-term behavior in a deterministic system that exhibits sensitive dependence on initial conditions. Now there's a lot of jargon in there, and so let me underline some of the jargon words that we should talk about just for a minute. Well, there's aperiodic, there's long-term, deterministic, and sensitive dependence on initial conditions. Okay, so aperiodic, of course, means not periodic. And in particular, we don't allow something trivially periodic that is just an equilibrium point that has a period of 0. So aperiodic means some kind of behavior that doesn't settle down to equilibrium and also does not repeat periodically. Next, long-term behavior. Now, not everyone would agree that this is an important part of the definition, but I'm referring here to kind of self-sustained chaos, that is chaos that even in the long run stays aperiodic. Not just transient chaos, in other words, but even after a very long time, this kind of behavior will persist. Deterministic means no noise, no randomness of any kind, nothing probabilistic in the model. It's just a model that if you use the same initial conditions, you'll get the same behavior every time. That's what I mean, that the present determines the future. And if you had perfect information, it would determine the future for as long as you could integrate. But of course, you never really do have perfect information, so that's what's related to this unpredictability that we talked about in the last lecture. And then finally, sensitive dependence on initial conditions, we said means that rather than trajectories emanating from nearby initial conditions separating algebraically fast, say linearly or some power of t, instead it will separate exponentially fast on average, which is considered very explosive growth of errors, and so therefore sensitive dependence on initial conditions. So like we earlier saw something called quasi-periodicity. If you remember, on a torus, that was aperiodic. It was also long-term, and it was in a deterministic system. But it's not chaos because it doesn't exhibit this exponential separation of trajectories. The trajectories only separate proportional to some power of t. Actually, just linearly in t for quasi-periodic systems. So that's why quasi-periodicity isn't chaos. And I don't know, do you want to ask anything about any aspect of this conceptual definition? Another way of saying sensitive dependence is, as I mentioned, that there's a positive Lyapunov exponent. All right, well, so now another word that we keep using is attractor. And I guess I should say, on all these definitions, there isn't uniform agreement in the literature. You'll see different books or teachers saying different things. So I want to try to bring that up here with the case of attractor. What are some of the issues? Pretty much everybody would agree, I think, that an attractor is an invariant set. That is to say, if we think of the attractor as a set of points A, that if you start in A, you'll stay in A forever. So that's what we mean by invariant. Now, an attractor has that property. It should also have the property that it attracts an open set of initial conditions. So I'll use the abbreviation IC for initial conditions. That's a little technical point that we'll talk about in a minute. Why do we need that? And also an interesting recursive thing, which is that no proper subset of A so let's call the attractor A. No proper subset of A satisfies 1 and 2. So let's try to unpack some of that. That is, this third one is often called minimal. That is, the attractor is minimal in the sense that it satisfies, it's the smallest set that satisfies 1 and 2. So I think this example will clarify it a little bit. Let's look at, suppose I had a phase portrait that looks like this in 2 dimensions. So we're not talking about chaos at the moment. This is just to clarify what I mean by an attractor. Suppose I have a stable point here and a stable point here, a saddle point here, and a simple flow that, whose phase portrait looks like this. So everything goes to one of these 2 stable points. Let's suppose the x-axis is invariant, so we flow like that along the x-axis. I said everything goes to one of these 2 stable points. It's not quite true because you notice the y-axis consists of initial conditions that would go to the saddle point here. So now, in a picture like this, what are the candidates for attractors? Let's think about that. Let's say, for instance, how about we look at this saddle point? Is that an attractor? So looking at the list, is it an invariant set? Yes, if you start at the saddle point, you stay there. Does it attract an open set of initial conditions? No. What does it attract? It attracts this closed set, the y-axis. Closed, okay, so what are we talking about? Open and closed. Remember in topology or analysis, they have the concept of, say, an open set. I don't need it in the most general context. Just let's say an open set in the plane or in R3 means a set with the property that each point in the set can be surrounded by a little ball, an open ball, meaning it doesn't contain its boundary. In the case of the plane, it would mean the problem is that if I want to put a little open disk around this point, the disk doesn't stay contained. I mean, the disk is not contained within the y-axis. Part of it hangs over to the side. So this is not an open set. Obviously, it's just a line. A line is not an open set in the plane. So that's the problem. Obviously, you don't want to call a saddle point an attractor, and it's not, because it violates the idea that it attracts an open set of initial conditions. You with me on that? You want to ask anything about that? Okay. Now, what about, how about the whole of the x-axis? Because if you think about it, so all right, so what did we conclude? The origin is not an attractor. Because that violates 2. How about the x-axis? Well, I mean, if you think about it, in the long run, everything ends up on the x-axis. So you might say that's good. I mean, in a sense, that set is attracting everything. Should we call that an attractor? Well, all right, let's look at it. Is it an invariant set? If you start on the x-axis, do you stay there? Yes. So 1 is satisfied. Right? If you start on the x-axis, you will stay there. Does the x-axis attract an open set of initial conditions? What do you think? Yes, it attracts everything in all of R2. No matter where you are, you will end up on the x-axis, or asymptotically approach the x-axis. So, and the whole plane is an open set. Any point in the plane can be surrounded by a tiny open disk that will still be part of the plane. So, yes, 2 is satisfied also. Now, what about 3? Are there any proper subsets of, sorry, the x-axis. Are there any proper subsets of the x-axis that would also satisfy 1 and 2? Yes, that's the problem. That is, an attractor shouldn't contain smaller objects that are also attractors. And that's the problem. 3 is violated for the x-axis because the things that you would think of as attractors, which are these 2 stable points, those are the actual attractors in this example, not the x-axis. Something like the x-axis is sometimes called an attracting set to distinguish it from an attractor. So it's an attracting set, but not an attractor because it's not minimal. But now, I said that each of these points are themselves attractors, so let's think about that for one little moment, although maybe it's very clear. So the stable points, if you start at one of those stable points, you'll stay there. So 1 is satisfied. Does it attract an open set of initial conditions? Well, what does this point attract? The whole right half plane, the open right half plane, right? Meaning the right half plane not including the y-axis. So yes, it attracts an open set, the right half plane, the open half plane. Yes, it satisfies 2. Now, does it have any proper subset that's an attractor? Well, what could be a subset of a point? I suppose the empty set, but that's not one that we want to consider an attractor. So 3 is satisfied also. So that's an attractor, and so is this point, an attractor. Okay, so any question about that example? Yes?
So do attractors have to be points?
Do attractors have to be points? No. Attractors could be limit cycles. So if we did the example of, say, a simple, stable limit cycle like this with an unstable point inside it, and suppose everything is attracted to that cycle, then you could ask, what is it invariant? Yes, if I start in the limit cycle, I stay there. Does it attract an open set of initial conditions? Yes. What does it attract? Do you know? I want to think about that for a second. What would be attracted to the limit cycle in this example? Everything? Everything except the origin, right? Because there's an unstable point at the origin. Unstable points are invariant, so you have to watch out for them. This would attract the punctured plane, right? The whole plane minus the point in the middle, and that's an open set. And is it minimal? Does it have any proper subset that satisfies this? No. I mean, if you think about it, like an arc of the limit cycle will not be invariant. Yes?
So if it only attracts everything that is inside the limit cycle, then would it still be, say, attracting an open set?
Well, that's an interesting question. So the question was, suppose it only attracted from the inside. Like suppose it was a half-stable limit cycle. Right? We've seen those are possible. That's interesting. If it was half-stable like that, it would be invariant. It would attract the open punctured disk inside of it.
Wait, would that count as open now? Would it not include the cycle itself?
Ah. Oh, that's interesting. Very good. The question was, what would be the set that it attracts? That is, points which, as time goes to infinity, are either on the cycle or asymptotically approach the cycle. And the astute comment, because I was about to run into trouble here, the astute comment was that, what does this attract? It attracts itself and the punctured region inside. And that is actually not an open set, because it contains its boundary. And if you looked at a boundary point and draw a little disk around a typical point, that point hangs outside of the set. So this would not count as an attractor. A half-open cycle is not an attractor for this reason. And of course, it better not be. I mean, you wouldn't want to call that an attractor. Yes?
But the inverse is an attractor, so we had
The inverse?
an unstable limit cycle with a stable node. That would be
The question was, if I had an unstable cycle with a stable spiral point inside, let's say, what one are we asking? Is it an attractor? The point in the middle? Yeah, it is. It attracts this whole open disk. Yes?
But in the definition, I mean, you wrote that it attracts an open set of initial conditions. So why can't I say I take an open subset of that?
No, I don't mean it attracts some open set. I mean the set of all initial conditions attracted to it, that is to say its basin of attraction, is open. Yeah, sorry if the language was ambiguous up there. The question was, you could find some open set that's attracted here. Say, pick this little open set. But that's not what's meant. It means the largest open set that's attracted is, the largest set that's attracted is open. The basin, the set of all initial conditions whose trajectories are attracted, that's an open set. All right, I don't want to dwell too long on it, but so you can see it's a kind of interesting set of properties. But some people add a fourth property. Now, not everyone does. Depends what you want to prove. So let me add I guess I would say it's more conventional to add this fourth property. which is going to be slightly technical. Let's talk about it on a fresh board. So the fourth property that is usually added, some people, I really mean some authors or some mathematicians, also require that trajectories that start near A stay near A for all time. You know, all positive time. So think about that. That's a little different from saying this. When I say it attracts an open set of initial conditions, when we talk about attraction, we're talking about what happens as time goes to infinity. That is, you don't really care where the trajectories go in the short term as long as they end up close to A. That's what property 2 is taking care of. But this is a kind of control freak additional requirement, which was, I don't want you going away from A ever. I mean, not far. Like, you know, a parent might say to a child or something, that you're going to have to stay close all the time, not just you have to end up with me at the end of the day. So let's look at this. Okay, I want to say it a little more precisely in case you don't know what I mean by this. This may be too precise for some of you. You would say it like this: given any neighborhood U of A, there exists some other neighborhood think of U as like a little sleeve sitting around A. That is, it's a very tightly constricted. You're trying to stay close to A. So think of U as just something fairly close. Like schematically, if this is A, maybe, you know, U is this larger thing sitting around it. So given any neighborhood U of A, there exists a neighborhood V of A such that if you start in V, that is, if you pick an initial condition, in U, no, I did mean V. Pick an initial condition in the neighborhood V, you'll stay in U forever. This is sort of in the spirit of, if you want to stay within epsilon, you must start within delta or something like that. So, but the key being this idea of staying in forever. So if you don't see what's going on here, let me show you an example that I hope will clarify it. Let me come over here and do it. Let's look at this phase portrait. This is supposed to represent a one-dimensional loop. So there is no region inside. Forget that it looks like this is a boundary of a disk. I'm just talking about a thread which is tied into a loop. Like when we talked about vector fields on the circle. So this would be I'm interested in a particular vector field on a circle that has a half-stable point. And so the flow on the circle is to go this way, come around, and then approach that point from that side. So if you wanted to write it concretely, it would be something like theta dot is, let's see, it has an attractor at pi over 2. So maybe something like 1 minus sine theta. Would that work? Maybe so. Yeah, I think that might be a vector field that looks like this. Okay, so there's a fixed point at theta star equals pi over 2. And we could ask, is this point an attractor? So let's think about it. If you start at this point, will you stay there forever? Yes. It's a fixed point. Does it attract an open set of initial conditions? Well, what does it attract? Everything. Right? No matter where you start, you're going to eventually end up there. So it attracts the whole circle, which is open. Does it have any proper subset that satisfies 1 and 2? No, because it's a point. So by my original 3 criteria, you would say that this point was an attractor. But some authors don't like that because they say, come on, I mean, it's sort of half unstable. If I start here, I'm going to go on this very big excursion through phase space before I come back. So I did not stay close to this point. If I put any tiny neighborhood around this point, I will leave that neighborhood before I come back into it. So this is the child that wanders off before it comes back. And so those authors would say, no, this is not an attractor for that reason. It doesn't have good control for all time. And so, take your pick. Depends what you're trying to do, whether you want to include 4 or not. Anyway, is that clear? Any question about this? So then the last thing to say is we've talked about chaos and attractors. Let's just say, what do we mean by a strange attractor? And so that would be, well, strange attractors, as opposed to, say, a point or a limit cycle or a torus. A strange attractor should be, well, there are various ways you could say what this is, too. Some people would say it's an attractor that exhibits sensitive dependence on initial conditions. So we could say it that way. It's an attractor with sensitive dependence. But other people might want to emphasize the geometric aspect, like I was hinting when I said a point or a limit cycle. You might say it's an attractor whose local structure is fractal, as opposed to smooth. So when we get to the fractal part of the course, you'll see, what I'm talking about in more detail. But this is emphasizing the dynamic aspect, the sensitive dependence, whereas this other concept is emphasizing the geometric aspect, the structure of the set itself. So sometimes people will say the thing I've written is called a chaotic attractor, whereas the second thing I mentioned would be called a fractal attractor. So the literature is fairly diverse on this point. Okay, I think I'm going to leave these definitions now and go back to what happens on the Lorenz attractor. Yes?
Sorry, could I just ask, you mean that the set itself has a sensitive dependence?
No, this question was, does the set itself have sensitive dependence? I mean the set regarded as an attractor for a dynamical system. So I'm saying that this is an attractor for a dynamical system which has sensitive dependence on initial conditions. Yeah. And it might raise questions in your mind. Can a system have sensitive dependence on initial conditions but not have a fractal attractor? I think there are examples of that. So they're not identical concepts, the fractal or the chaotic concepts. Okay, but anyway, we're not ready to get into that yet, since we didn't talk about fractals yet. But instead, let me go back now that we have some of these words and talk about the Lorenz attractor. Yes? Couldn't a chaotic system also have other non-strange attractors? Yes, it can. Right, so it could be chaotic for, it could have a basin of attraction for the chaotic attractor, and it could also have a basin of attraction for other attractors. They could be coexisting attractors. Is that what you have in mind? Right, I'm saying that within the non-chaotic attractors, you wouldn't. Well, would you call such a system chaotic? It's potentially chaotic. It depends where you start. Yeah. Yeah. There's a lot of possibilities here. to have disagreements. Like some people think the important part about chaos is the sensitive dependence, but not the long time behavior. Like when you roll dice, if you think about it, any game of gambling, roulette or dice, those are, to a good approximation, deterministic systems, yet they're unpredictable. But in the long run, they're totally predictable. The dice will stop moving. Right? So the dice come to a fixed point, but they have this chaotic transient before they get there that makes it hard to predict what they're going to do. So would we call that chaotic? I mean, the long-term part is not chaotic, but so I like to reserve the word transient chaos for that. And those are unpredictable systems. It's transient chaos that causes unpredictability. And if you have long-term chaos, that's just as good. I mean, that's even more so unpredictable. Anyway, let's go back now to talking about the Lorenz attractor. That is, we drew some pictures of it in the last lecture on the computer and saw, you know, sort of to just arm wave for a minute that trajectories moved around in a spiral on one eye or one wing of a butterfly shape, and then they darted over here and spiraled around, and then they shot back. And it was doing this kind of thing over and over. But how to describe that? So this is section 9.4 of the book. And I want to show this clever thing that Lorenz did where he reduces the dynamics to a one-dimensional map. And so we're now beginning a transition into the next part of the course where we try to look at simpler models of chaos than the Lorenz system, namely these one-dimensional iterated mappings. And it's right there in Lorenz's paper. He's doing that in his paper as part of his way of thinking about his problem. So let's discuss exactly what did he do. If you look at figure 2 of his paper, by the way, you know I posted his paper on Piazza, so I should be reading that. And also read the chapter about what Lorenz did from James Glick's book, Chaos. Anyway, so Lorenz at some point looks at his figure 2 in his paper, which looks sort of like this. Figure 2 in Lorenz, 1963. He's looking at Z versus Y, some projection of his attractor. And, you know, I'm not going to try to really draw in detail what he has, but he has something that kind of looks like this. There's some trajectory kind of spiraling away slowly from some point. Then it shoots over to here, goes around, you know, spirals around here, comes back, and so on. It's doing some complicated thing. Trying to make it look a little three-dimensional. Anyway, so he's got that, and he's working at the standard parameter values. So he's, as always, he's got R equals 28, sigma equals 10, and B equals 8/3 in his equations. If you remember the Lorenz equations, they had those 3 parameters. So anyway, and then he makes his comment, which I just want to read to you. I'm not going to try to write it down, but you got to really listen to it carefully because he's describing something here. Okay, so he says, in looking at this trajectory, he says the trajectory apparently leaves one spiral only after exceeding some critical distance from the center. Now, what that means is, here we are, we're spiraling. He would say we haven't left the spiral until we got this far out, then we leave and go over here. And he's thinking it's kind of because we've exceeded, like he's imagining that there's some little circle around this point. Not little, there's a circle around this point or something. Once you get outside there, it's time to go over here. That's what he means when he says it apparently leaves one spiral only after exceeding some critical distance from the center. Once it does that, now it's over here. Then he says the extent to which this distance is exceeded, that is how much we're outside this special critical region, The extent to which this distance is exceeded determines the point at which the next spiral is entered. So in other words, depending on how far out we are past this imaginary boundary, that controls where we're going to land over here. And then he says, and this in turn seems to determine the number of circuits to be executed before changing spirals again. In other words, what he's struggling to do here is he's trying to find a very reduced description of what's going on. And his attempt to do it is he's thinking in terms of a distance from the center of a spiral. And he says that the distance from here when I leave determines where I enter, which will then determine how many loops I make here before I leave again. And that'll then control where I enter over here, and so on. So then he comes to the punchline, which is, he says, it therefore seems that some single, underlined, just by me, not by him. He's not the kind of guy who would ever shout. He was very quiet, modest guy from Maine. You could barely hear him talk, actually, and he had a real monotone. And you would sort of think like, you know, I feel hungry, I want to go to lunch or something. Like, he was not captivating. Except he was fantastic. Because what a great scientist, and also a really sweet person. But anyway, he was, I'm going to talk about my sister. No, I'm not going to imitate him. But he didn't have an entrancing voice. And so anyway, but pumping up what he might have said, he says, it therefore seems that some single feature of a given circuit should predict the same feature of the following circuit. In other words, one number that characterizes this circuit will characterize the next number that defines something about this circuit. And so rather than talking about three continuous numbers in time, we're going to just talk about one number in discrete time, that is from one spiral to the next. Yes? I'm going to tell you what sort of number. At the moment it's vague. This is intuition. This is creativity that you're trying to follow. Right? He's got this vague creative idea that there's some single number that controls everything. So anyway, that's it. It seems some single feature of a given circuit should predict the same feature of the following circuit. Now if you think about what's happening here, when do you leave? You leave after you reach a maximum of z, and then you shoot over here, and then you spiral around, and then you reach some other highest point, and then leave. So he gets interested in the maximum of z. That is, he looks at a time series. Say I looked at z as a function of time. And you know, when you're spiraling in this outward spiral, it's going to look like some kind of growing oscillation. And you've seen those in dynamics of the Lorenz system. And so he defines the nth maximum as a point of interest. So, you know, say this is the, actually I'll just call that one Zn. And then let's compare it to the next one. That's Zn plus 1. And then at some point, you know, I jump over. And then again, I can look at, you know, here's a maximum, here's a maximum, here's a maximum. I just keep doing that as I look in the series. And so the definition is that Zn is the nth relative maximum, or a local maximum, whatever you want to call it, of the function z of t. And so his idea is then, how does z sub n determine Zn plus 1? He thinks it does. And that's what he decides to graph. So he's led to look for this relationship between Zn plus 1 and Zn. And so that's what I want to now show on the computer. He shows a picture of it in his paper, but let's actually generate it. Yes? The question was, is the period of the oscillations fairly constant? It is fairly constant, as you'll see in the simulation. It's certainly not really constant, but it's not wildly different either. So let's see if I can get the computer to work. And let's put the screen on. Okay. And I want this down. So we've used interactive differential equations before. You can find it on the web. Just search for interactive differential equations, and it's the first thing that pops up. And then within the menu, actually, let me make it sort of dark in here, because what you're about to see might not be so easy to see with the lights on. So, I don't know. Ready? Let's make it really dark. Oh, yes, good. Thank you. That might help, too. I don't know if we really have to do that, but why not? Okay, so let me scroll down to, under chaos and bifurcation, under the Lorenz equations. We've looked at some of these other little applets, but let's do the one Z-max map. And you'll see that it's already starting to run. That is, oops, let me go up a little farther. What's happening here is, okay, so let me pause by just clicking somewhere on the screen. Here's Z of t. There was the question, is it sort of periodic? You can see it's, approximately periodic. We're drawing a blue line every time we go through a maximum. And the spacing between the blue lines is fairly constant, though certainly not really periodic. And then every time we go through one of these local maxes, we measure, so this is Z as a function of time. You measure the height and plot this height as input and that height as output. So here's input, Z max n versus Z max n plus 1. And you can start to see there's little blue dots falling on some kind of pattern. Now let me let it run for a while. Let me clear and you watch it again starting from the beginning. Also, if you can see them, I don't know if it's visible, the blue dots are hopping around fairly, not in any obvious way. They're hopping haphazardly. They're not sort of progressively filling out any shape. So let's let this run a bit. And the question is, does anything emerge? You might be able to see something. Are you getting a feeling of a pattern? You want to try to describe what you're seeing? How? Did the period increase in a certain place? It may have. The question was, does the period increase maybe because of a jump? Like, certainly when you're spiraling around one of the spirals, you might have a fairly constant period. When you jump all the way over to the other spiral, that's farther to travel in phase space. Maybe that takes a little longer. Anyway, I hope it's clear by now that these dots are falling on some kind of shape that looks approximately like, maybe sort of like an upside down absolute value function, or something. I mean, it has a, if I put my hands on it, you can see it's falling on something that looks sharp. It looks like it has a sharp point at the top. But what you really are supposed to notice is to what a nice approximation these points appear to be falling on a curve, a one-dimensional curve of some kind. That is, they could potentially be anywhere in the plane, right? They could be all over the place, but they're not. They're falling on this very tightly constrained set. And so Lorenz says that looks like a graph of a function. And so he's going to pretend that there is some underlying function with this shape and that the dynamical system is just sampling that function. So let's explore the implications of that next. Is there any question before I turn off the computer? Yes?
So there's one point that we had sort of, at least from close to the beginning, that seems off of that.
Oh, the question was, it seems like initially there was a point that was off the curve. Maybe this one here?
Yeah.
there's a little dot that does appear to be off the curve. Now, if you think about that, the initial condition might have been off the attractor, right? So there was no reason we started on the Lorenz attractor. So you're right, there will be a transient time before we get on the attractor to a good approximation. And for those initial conditions, then you'll have a few points that are not going to fit the pattern. But we don't care about them. We really want the long-term behavior. That's why I say we're looking at the dynamics on the attractor, not the approach to the attractor. And so Lorenz was doing this after a long time. So yeah, we would ignore this kind of point. Any other question? Okay, so I'm going to turn that off then and go back to full lights. All right, so he's led to look for this relationship between Zn plus 1 and Zn. And as we've just seen, the result is that interesting graph. That is, there's a graph that looks about like so. Zn plus 1 versus Zn. You may have noticed I drew a diagonal line in there, 45-degree line. And the picture looked about like this, maybe. Something like that. And so we're going to say that it sort of looks like Zn plus 1 is some function of Zn in the sense that there's essentially no thickness to the graph. That is, remember that this is not really, there was a cloud of points, but I'm saying the cloud of points appeared to fall on this, this curve. Now that's wrong, okay? I don't want to lie to you. There is no such curve. It looked like it, and Lorenz explored the possibility, but as we go deeper into the subject, we would understand that this is not really a single-valued function. In fact, it's not a function. At a given Zn, there's a little bit of vertical thickness here. So at a given input, there could be more than one output. And so it's not really a function. But you saw, I hope, in the computer, it was pretty close. And the question is, well, what if it was exactly a function? What would that imply? Yes? The question was, is this true for all initial values of Z? It's true for almost all initial values of Z. There are initial values that could lead, for instance, to a saddle point, and then they wouldn't be on the, you wouldn't see them doing chaotic motion. So this is true for all initial conditions in the basin of attraction of the strange attractor, which is almost all of them. And they always produce this picture. Yes. After the transients have decayed and you're on the attractor, you'll always get this same picture. Anyway, so let's suppose that there is this function, keeping in mind that it's not really right. But what would it imply? Well, the key fact about it is look at its slope. It may not be clear from the way I drew it, but Lorenz observes that the slope of this curve everywhere is greater than 1 in absolute value. That is, its derivative, f prime of z, in magnitude is greater than 1 for all z in the domain that he's going to look at. And a function like that has some pretty interesting implications. That is, if you think about what we've got here, we're saying you take a zn that produces the next zn plus 1, and now you could think of this as the next input to produce zn plus 2. It's like, you may have played that game with your calculator where you just press the cosine button over and over again, or the square root button, and you just want to see what it's going to do. That's what we're doing, except we're using this button, the Lorenz map button. We're going to keep pressing that over and over and watch what happens. So we'll iterate f of z to study the dynamics. And, well, let's first look at a very special possibility, which is there anything we can do where when we put in a number and press the button, we get the same number out again? That is, can we have a fixed point of this map? And as you can probably see, yes, we can, where it'd be where zn plus 1 equals zn, the input equals the output. And so I've conveniently drawn the line here where zn plus 1 equals zn. That's like y equals x, so to speak, in xy coordinates. The diagonal, the map, the identity. So this point here, that is this value zn, we're going to call z star because it acts like a fixed point for a differential equation, except now it's a fixed point for an iterated map in the sense that f of z star is just z star again. So the question was in the animation, that is in this applet we were just watching, we didn't seem to ever quite hit this point, because if we had, we'd never change. We'd just stay there. So let's talk about this point. Did you want to say something about that point? No. Well, you raise an interesting issue. What about that point? I mean, could that point be an attracting point, for instance? It doesn't seem like it was. We didn't see it. And Lorenz analyzes the stability of that point and shows that it's unstable, which is why you're not observing it. But before we talk about the stability of that point, let's not forget that this is a shorthand description of motions in the three-dimensional space. And so what does this fixed point mean as a trajectory in the original Lorenz system? It's sort of interesting. How could you have a trajectory where the nth relative maximum is the same as the n plus first, given that on a spiral, on one of the wings, you keep increasing the z? How could you get a result that stays the same? Maybe you can, you're drawing it with your hand.
You could have
A figure 8 on its side, right? That's what you want. So something that goes like this, and then over, and then comes back, that could have a zn and a zn plus 1 that are the same. That is, they'd be the same height. So that interesting loop, which is a possible loop on the Lorenz attractor, would correspond to this fixed point. Good. So that's what we're talking about now. And this is a conceivable periodic orbit of the Lorenz system. Is it stable? That is, here's a limit cycle. Is it a stable limit cycle? Well, no. And so the argument is pretty easy. We know how to analyze stability in systems. We can either use graphical methods or we could do linearization. And we could do either one of those here, too. Let's first do it with linearization. So let me let Zn equal Z star plus a small perturbation, which we'll call A to n. So we're thinking of A to n as some tiny number. And then we want to linearize about Z star. So we'd go Zn plus 1, which by the definition of eta should be regarded as Z star plus the next eta, so A to n plus 1. But on the other hand, Zn plus 1 is f of Zn according to the Lorenz map. And f of zn would be then f of z star plus a to n. And so far everything is exact, but then here's where we linearize and say, so expanding in powers of the small eta, we'd get f of z star plus a to n, f prime at z star, plus then there would be quadratic terms in eta and or higher, and we're just going to ignore those because we're doing linearization. So we'll ignore those. And then also notice that by definition of z star and f of z star are equal, so we could cancel them out. And so we're left with an equation for eta, which says tells us how the deviation eta grows or decays with each iteration. So we're getting eta n plus 1 is approximately, that is if I neglect the higher order terms, f prime of z star eta n. And now that's easy to analyze because we're just asking, does the deviation grow or decay? Well, just take absolute values. I mean, recall the key fact, the one mentioned above, which is that f prime of z star in magnitude is greater than 1. Why am I saying that? Because f prime is greater than 1 everywhere in magnitude, not just at z star. Its derivative is everywhere greater than 1, at least visually by looking at the graph in the computer. So that's not proven, but that's just sort of empirically what appears to be the case. And so if f prime is greater than 1, then that in magnitude, that tells us eta n plus 1 in magnitude is greater than eta n in magnitude. That is, deviations are growing, which means that's an unstable point. So this is how Lorenz argues that z star is stable. But then, as I say, you could also, rather than do it with linearization, you could think about it graphically. And there's this nice graphical construction you can do, which people call cobweb diagrams, because they sort of look, for someone who hasn't spent much time with spiders, and first of all, it's a spider web, really, not a cobweb. It's not just made from dust. It's some anyway. It's a construction that sort of looks like something that a spider might make. That is, here's the map, or the graph of it, the map, and then you could ask, what if I'm at this point but a little bit off? So suppose I'm okay. Like if this is z star here, what if I start a little bit to the left of it? This was z star over here. So okay, well, so here's a point, and now to figure out where it goes, you just go vertically till you hit the graph. So you would go like this, doink, now you're there. Now, okay, so that's your new output, which is this. And now where does that go? Well, that is not in any position to go anywhere because we want to make it an input, not an output. And there's this clever move where you can go like this until you hit the diagonal line, because the diagonal line is where outputs get converted to inputs or vice versa. So in the cobweb construction, you go like this vertically till you hit the curve, then horizontally till you hit the diagonal, thereby making the new input this height, except now it sort of lives down here. That is, you go like that. And so I would go up to the curve, or vertically to the curve, it could be up or down, horizontally to the diagonal, vertically to the curve, horizontally to the diagonal, vertically to the curve, and so on. You just keep marching around. And, you know, this is how you can iterate graphically. So there's a lot of lines there. I hope you can see what's going on. But anyway, this is the part that supposedly looks like a cobweb, this construction. So always horizontally to the diagonal, vertically to the curve. That is vertically to the graph of f of z, and then repeat. So anyway, doing it that way, you can also see that it's plausible that you will not actually have a stable point there. But this picture might have led you to think, actually, could the cobweb close? Like, could I go around a certain number of times and then make a closed shape? You could imagine that's possible. I don't know if I dare to try to draw one. But, you know, rather than being a fixed point, could I have something which, all right, so I might have to fudge a little here to get this to work. What did we say? We're going to go vertically to the curve, horizontally to the diagonal. I have no idea if this is going to work. Okay, here's where I can fudge it. So, well, no. No, maybe not. I was going to go, right? If I had that, if that worked, okay, I'll make it work. Like Tim Gunn says on Project Runway, make it work. Make the diagonal work. There. Okay. So there. So now that's a periodic orbit. You know, not, yeah, that works. So the next question is, can there be periodic orbits that are stable, even if the fixed point is not stable? And so let's look at that for a second. Well, now, how would we describe this periodic orbit? What's going on there is we have a sequence of points. So it would give some kind of sequence, like say Z1, Z2, Z3. With the z's repeating after a while, that is, Zn plus p would equal Zn for all n, where p is the period. So like in this example that I drew above, let me see. I started somewhere. I called that 1, go up 2, 3, 4, and then it looks like on the 5th time I'm back. Is that right? Should I count? Maybe I'll count again. I'm not sure what. Sorry? Did I not count right? So if this was Z1, then I go up to here, I'm over to here. This is then Z2. There, that's still Z2. Now I'm here, that's Z3. Go up, go over to here, this is Z4. And now I'm back, so now it's Z1 again. So Z5 equals Z1 in this case. So this would be, by our definition, this would be called period 4. Right? Because Z1 equals Z1 plus 4, Z5. So P was 4 in our example above. Anyway, so we now want to explore the possibility of these periodic orbits and ask, could they be stable? Just to make sure you're not losing the big picture. Why are we doing this? Remember, Lorenz is asking the question, could his attractor actually just be a stable limit cycle? Or actually, you know, we earlier said there are no stable limit cycles for the Lorenz system at these parameter values. How do we know that? He says, well, if there were a stable limit cycle, it would have a Cobweb diagram that would give a set of points obeying this kind of periodicity condition. And let's now examine whether such a thing is stable. And he'll show that it's not. Again, because of the slope of f. That's the issue. So let's work that out. That is, if we think about this equation, where we iterate p times, if you think about this, something like Z2, which is f of Z1, then Z3 would be f of Z2, which is f of Z1, which it'll be convenient to write as the composition of f with itself twice, that is f2 of Z1. This doesn't mean f squared, it means f of f. And, you know, if you keep going, doing this sort of chain of equations, you would see that Z4 is, or you'd have to do f 3 times f of f. It'll be f3 of Z1. And it's just worth thinking about it this way, because what you'll then conclude is that something like Zn plus p can be regarded as doing f p times applied to Zn. That is, notice that these numbers add up. 1 plus 3 adds up to 4. So this is handy to look at it this way. That is, instead of thinking about, all we have to really think about is the function f or its repeated composition with itself. And so the definition would be that z is a point of period p, a periodic point of period p, if it satisfies some equation like fp of z is z. Okay, so this is a generalization of the idea of a fixed point. A fixed point would be something of period 1. F of z is z. A period 2 point would mean f of z is z. It repeats after 2 iterates. And in general, period p point is something that repeats after p iterates of f. And p is supposed to be the smallest integer with this property. Otherwise, it's, I mean, something that repeats every 2 will also repeat every 4. But, so p is the smallest positive integer with this property. Okay, so we have the idea of a period p point, and what we want to conclude with is to say that all period p points are unstable. Just like the fixed point was unstable, any period p point is unstable. And the proof is pretty easy. Let me just show you how to do it for period 2, and then you'll see how to do it for any period. That is, so period 2 would be unstable because we'd have to look at a point. I mean, suppose we have the map, well, like if we had f of z equals z. So we have period 2. we could then go through our same linearization argument and ask, is this stable? Now, when we did the linearization argument, remember what we ended up doing? I mean, look here at this top board. At the top board, we showed that the deviation is just controlled by f prime at the point z in question. So now we'd be asking, rather than f prime, we're looking at the derivative of the function that's operating, which now is really the function f2. Because, I mean, this is a nice way of looking at it. If we have a point of period 2 for f, then it is a fixed point for f2. Right? f2 of z is z. A point of period 2. So a period 2 point for f is equivalent to a fixed point. This is a principle we're going to use a lot in the next few lectures, that a period p point for f is a fixed point for f to the p, or in this case for f2. And so we already know how to calculate stability of fixed points. We just look at the derivative of the function and ask, is it greater than 1 in magnitude? That controls the stability. So our calculation will boil down to asking, what is the derivative of f2, rather than the derivative of f itself? And the derivative of f2 is something that you know how to do from freshman calculus, because what I'm asking is, what's d dz of f of z? And by the chain rule, it will be f prime of f of z times f prime of z. And now the key issue was, since this is the thing that controls the deviations, whether they grow or decay, we want to ask, what's the magnitude of this derivative? Is it greater than 1? And the answer is yes, it's greater than 1, because if I look at the magnitude of this, it'll be the magnitude of this, which is the magnitude of this product, which is the magnitude of each term separately, multiplied together. That times this. And now the punchline is, we said f prime was greater than 1 in magnitude everywhere. So this is greater than 1, and this is greater than 1. And so this product is greater than 1. And so that tells us that there is no stable period 2 point. And by the same argument, except with p factors instead of 2, you will conclude that there is no stable periodic point of any period if f prime has the properties that we said. And so this is the argument that Lorenz gave for why there are apparently no stable limit cycles in his system. And again, it's not a correct argument because f is not really a function. But if it were, that would be a proof. Now, making it into a proof is something that occupied people for a long time after his work, and the proof did not use this idea, it used other ideas. But anyway, I want you to at least appreciate there's good reason to think that there aren't any stable limit cycles. And so with that as our transition, now in the next lecture, we're going to start exploring these iterated maps in much greater detail. Okay, so let's stop there.